Thank you so much for that very, very nice introduction. Just make one little correction with the Breakthrough Prize. I didn't give away all my money for that prize. I gave some, but anyway. Thank you very much for the great honor of being the Madison Medal recipient this year. I mean, it means quite a lot to me because Princeton really was a turning point in my life. So as already the introduction said, I grew up in Australia and had a rather complicated early education. I skipped a lot of grades. When I was in primary school, I took my math and science classes at the local high school. When I was at high school, I took my math and science classes at the local university, Flinders University. Yeah, my mother had to drive me quite a lot every day, actually. Yeah, but you know, I didn't really take my studies seriously as a kid. You know, I viewed it as a kind of a game. You know, that if I enjoyed the subject material, I paid attention. If I didn't, I would doodle and sort of zone out. Still, my mentors at Flinders recommended that I study abroad, and somehow I got into Princeton for graduate study at age 17, as already said. Yeah, so at age 17, I didn't have that many life skills. My father had to come with me and teach me basic things like how to do laundry, how to open a bank account. But you know, it was very welcoming here. I bonded a lot with the first year math and physics students. We did everything together, really. Yeah, I had a great time, actually maybe too great a time in some ways. Played a lot of bridge, a lot of foosball, a lot of computer games. I discovered the internet. That was, and I didn't pay that much attention to my classes, to be honest. Yeah, so this came to bite me about 2 years in when, so Princeton's math department has these infamous general exams. They are terrifying 3-hour oral exams that every graduate student has to take, and everybody studied like for months for them, except for me. I just thought, okay, a couple of weeks of review would be enough. And basically, I passed, but only by the skin of my teeth. They were asking easier and easier questions in my field until I could finally get enough right that they could pass me. But it was really a shock because this had not happened to me before. And my advisor, Eli Stein, had to give me the talk. Right? That he said that I came here with like glowing letters of recommendation, that they had high expectations, and I wasn't living up to my potential. And yeah, so basically I had to get my act together. And so, you know, for the first time, I really sort of did, you know, I did not want to disappoint Eli again. And, you know, I spent the last 2 years, actually, well, I still played a few computer games, but I actually did, you know, try to study math and actually, you know, do what I was supposed to do. And I got my PhD. And I got a postdoc at UCLA, which was amazing. I've loved it, and they've kept me. I've been there for 30 years. You know, I still kept in touch with Princeton. I visit frequently, kept in touch with Eli until he passed away a few years back, unfortunately. And one thing that Eli impressed upon me is that, you know, you're not just here in math to, you know, prove your theorems and you know, just play with math puzzles, you know, that, you know, service is also important. And of course, it's a core value here at Princeton. And, you know, you should always look for ways to serve the broader community and not just sort of live in your ivory tower, or fine hall, as the case may be. Yeah, so, you know, so I was always on the lookout for ways to live up to that. I did have the honor finally in 2021 to serve on President Biden's Council of Advisors on Science and Technology, where, you know, we convened with top scientists, industry leaders, government department heads, on lots and lots of pressing technology issues, you know, biotechnology, wildfire prediction, AI. And it really, you know, It was really, really fulfilling, I have to say. A lot of work, but really, really fulfilling. And I got to see just sort of the broader scientific ecosystem, and just how precious it is and how we need to fight to keep it. And I also saw just how the world was changing and how, math and science and technology will all be transformed in the coming years. And so now I'm back at UCLA. I serve as a Director of Special Projects at the Maths Institute there, IPAM, where I'm trying to set up experimental projects to actually see how math in the 21st century in particular is going to work. So that's what I want to talk about today for the rest of my lecture, because I think math is due for quite a bit of reform, to be honest. We haven't changed our practices that much in several centuries. We're one of the most conservative, not politically, but in terms of practice, professions out there. On the left of the screen is a textbook from a memoir, actually, from Cauchy, about 200 years ago, introducing what we now call the Cauchy-Integral formula and other basic facts of complex analysis. And maybe it's a little hard to see, but if you're a mathematician, the textbook looks almost identical to a textbook we would give our students today. I mean, other than that it's in French and not typeset using a computer. But, the equations and the way that things are laid out, we haven't really changed the way we educate our students that much. And we're maybe the last department left that clings to our blackboards. There's a photographer, Jessica Wynn, actually, who I know, who has a nice little coffee table book and just photographing the chalkboards of mathematicians as works of art. It's part of the way we do mathematics. And I have 4 blackboards in my office myself. I will not let go of them. But maybe we do have to change a little bit. So the other sciences, for example, are beginning to evolve with the times. So even before like the modern AI revolution, if you look at, say, physics or chemistry, say the number of collaborators that you see on papers has grown significantly, whereas mathematics we're still stuck at 1 or 2 on the average people that we work with. Not because we're antisocial, well, not completely because we're antisocial, but there are special issues that make collaboration hard in mathematics. There's a high barrier to entry. A lot of the problems we work on, you need a math PhD to even understand the question. And we have an extremely high standard of proof. Our arguments need to be 100% correct. And if you have a collaborator who supplies part of your argument and it has an error in it, the whole paper can be destroyed. And our workflows do not scale. So we love our blackboards, and it's an amazing experience to collaborate with someone who you're really sort of attuned to at the blackboard and just exchange ideas at a really fast rate. But if you're trying to work with 20 people, this doesn't work. So we may be missing out on sort of the industrialization of science that we see in other disciplines. But I think now, because of new technologies, we can finally do this. So in the last few years, we are beginning to do new types of mathematics. So one analogy I like to give is that in the experimental sciences, you make a distinction between case studies of an individual entity, like a single, say a single patient or something, or you can do a population survey where you survey like all the people in a certain demographic. And you do both. They both have value. But in mathematics, we kind of have only done case studies by and large. We take a single theorem, a single problem, and we study it intensively for a month or several months. But we don't take a population of 1,000 problems and do data analysis on that. We just haven't had the ability to do that. But now this has become possible. We're finally beginning to see broader participation in mathematics. As I said, you needed a math PhD even just to play the game. In the past, but there are now large math projects where we get contributions from undergraduates, high school students, people in industry, just regular people. And of course, we have all these AI technologies which are finally they're reaching the break-even point where they actually save more time than they waste. In math at least. Maybe I won't speak outside of math. So because math has one special property that maybe other disciplines don't have as much, is that we can check our answers very, very precisely, and even with a computer. And so in particular, we have this technology called formal verification that has become very mature in the last few years, where we can actually get a computer to check if our arguments are correct. And this is what allows these trends to actually become a reality. So I'll give you an example of this, which I've been involved in, and you may have heard of because it made a bit of a splash in social media if you follow kind of math Twitter or something. So it concerns a bunch of problems posed by the mathematician Paul Erdős. So collectively they're known as the Erdős problems. It's a collection of about 1,000 problems, and there's a website by Thomas Bloom, a mathematician at Oxford, at Bristol, who has collected all these and has a very nice website and community building around it. So Paul Erdős was one of the most prolific mathematicians of the 20th century. He authored over 1,500 papers in mathematics. I think that's still the record. I met him when he was 10, actually. I was 10, sorry. He wasn't 10. There we are. And so he just loved to give problems to people. I mean, problems was like his way of sort of encouraging people to do mathematics. He actually was one of the people, also the letter writers for me to get into Princeton, actually, just as another connection. So yeah, very grateful to him for that. He posed many problems, and he was also known for giving like small cash prizes for these problems. Well, not all of them, but some of them he said, I offer $25 for a solution to this, or $50 for a solution to that. A few problems he thought were extremely important, and he offered more. This is one problem which has been enormously influential. The exact math is not important, but does every large set of natural numbers contain lots and lots of arithmetic progressions? That's roughly what this question says. He offered $5,000 for this. Still open, but lots and lots of work has been done on special cases of partial progress. I have several papers in top journals, including Princeton's journal, the Annals, doing special cases of this, solving special cases of this problem. And so Erdős called these problems acorns, requiring deep or subtle new insights from which a mighty oak can develop. But he posed 1,000 problems, and they weren't all acorns. So there are some problems that are actually rather easy. So he posed another problem, can you solve this equation? Can you find a solution to n factorial equals x to the k plus or minus y to the k? If you know what Fermi's last theorem is, it looks which was also solved here in Princeton, actually. It looks a bit like that. So he posed this in like 1980, but it turns out that with a modern computer, you can search and it's wrong. Okay, there's a solution to this equation. Erdős called these marshmallows, serving as a tasty tidbit, supplying a few moments of fleeting enjoyment. So it's a very mixed bag of problems. But it's a list of 1,000 problems, and some of them are solved. I think currently about 400 are solved, 600 are unsolved. It attracted the attention last year of a lot of tech companies, actually, because the AI tools were becoming powerful enough to actually start making progress on these problems. There's been a lot of hype on like, oh my gosh, they're solving problems that mathematicians have not been able to do for decades, which is technically true. But what has happened is that basically these AI companies have kind of found all the marshmallows. That all the highest profile problems that we most want to solve, AI has so far not been successful. But the problems for which Erdős only posed once or twice, there hasn't been much literature on them. Some of them AI was able to find solutions which no human mathematician had the time or attention to look at. And actually, if you actually plot all the different attempts, the success rate of these tools is still about 1 to 2%. So it's just that there's just so many problems that out of the 1,000 problems there, they've managed to pick up like 20 of them to solve. But still, that is incredibly impressive. I mean, if you told me like 3 years ago that this would happen, I would not have believed it. This is genuinely an advancing capability. And so it's not helping us solve our case studies, the hard problems that we traditionally love to work on. But I think what this shows is that there is a different way, a complementary way to do mathematics, sort of math by breadth rather than by depth, where instead of working on one problem really, really hard, you sweep out 1,000 problems with your automated tools, and you just pick out and you try to identify all the problems that are susceptible to sort of relatively easy methods. And that actually works. And it's a capability that we didn't have before because we just did not have the manpower basically to do that. So it's starting last September, we actually started tracking how many of these problems are solved. So this is just a graph to illustrate what happens. So currently of the 1,000 problems, about 700 are still open, and about almost 500 are solved. Okay, there are some other plots which I won't discuss here, but the progress has been sort of relatively slow. There was a little bump about last October because AI tools started developing these things called deep research tools, where you could search the literature for any relevant paper that sort of matched a problem, even if you didn't have any keywords. It was sort of web search on steroids. These tools started picking up, solutions to problems so that they found problems that were listed as open on Thomas Bloom's website, but had actually already been solved in the literature. But we just did not have the capability to search and find them. So we already picked up like 10 or 20 solutions that way. Oops. But then there was a big acceleration starting around Christmas, actually, when the AI tools finally became some newer models of these AI tools came out, and they started solving quite a few Erdős problems, maybe like another 20 or 30, actually. And then they stalled, actually. I think they in the last few weeks, we haven't had this incoming flood anymore. So maybe this phase of the story is complete for now, but maybe with the next iteration of these models, we'll get another surge. Okay. By the way, in case you're wondering about this big spike here, that's because at some point Thomas discovered this big list of Erdős problems that he didn't know before, and he added 50 more problems to the list. Okay. All right. So I'll just give you one or two examples. I mean, I know many of you are not mathematicians, so these are just very high-level sort of examples of how humans and AI have been able to solve these problems, often by some combination. This is Erdős problem number 367. It's asking, well, okay, can you find a number n such that a certain function of the prime factors of n plus 1, n plus 2 obeys a certain inequality. Okay, so the precise thing is not important, so back in 2025, so Thomas has this website has a little discussion forum. Every problem has a little web forum underneath where you can make comments. And one of the participants of this forum just said, I think I can solve this problem if I can show a certain auxiliary equation. So he proposed a counterexample to this inequality, and he said, I'll substitute in a specific choice of n, but I needed to check a certain congruence, which he could check by computer the first few values, but he couldn't prove. And then he could solve the problem. And so I was reading that site, and I just been playing around with AI, so I just plugged in that problem into an AI tool, and it just said, yeah, here's the proof of this congruence. Okay, and you use the p-adics, and you do blah blah blah, and it just solved the problem in one shot, which I found quite impressive. The proof was actually rather verbose and unnecessarily complicated. I did actually simplify it, and then I explained on the forum how to solve the problem, and then another participant decided to feed in that plain text English argument into another AI to convert it into a formal proof that can be verified by one of these formal proof assistants. So this problem, or at least one part of the problem, is now solved, and the proof is actually has been completely verified in one of these computer languages. The language is called Lean in this case. So that's one example. Another example is so there's a more complicated problem. Okay, so maybe I used Nano Banana to illustrate what the problem is. So rather than give you the math, I'll give you a little game. Suppose there's two players, Alice and Bob. Alice has a pile of coins, and Alice will split the coins into, let's say, 5 piles of coins. And then Bob will select some of those piles. But the rule is that Bob can only select a sequence of piles that are either increasing in height or decreasing in height. So Bob cannot select these 3 piles, but he could select, say, these 3 piles because they're increasing or decreasing. And Bob will, of course, select and he gets to keep all the coins that he selects. So he wants to get the most coins. And Alice wants to arrange the coins so that Bob takes the least amount of, Bob cannot take as much of her money as possible. And the question is, what is the fair price? Well, how much should Alice charge Bob to play this game? So that is one way to describe this problem. It has no practical application, but this is a very typical Erdos problem. So one of the participants on this site did some numerical calculations and started to conjecture what the answer should be. I'm getting short on time, so maybe I'll skip some of this. But using an AI, actually, at least a special case of this problem was solved by converting it to, so unexpectedly, this coin problem, converting it into a problem about packing little squares into a big square. There's this trick, which we were amazed when we saw it, that the AI came up with it. Later we found that this trick actually appeared in a paper back in 1959. But it was new to us. And so we were able to solve at least a special case of this problem when the number of coin piles is a perfect square. And then I use another AI tool to then explore what happens if, in general, when the number of piles is not a perfect square, and we were able to figure out sort of what the optimal configurations of coins were, and this led to a conjecture for what to do in general. And then another participant observed that this new conjecture, when you put it in square packing language, was actually equivalent to another problem on the site, another Erdos problem, which had just been solved. There was a paper like 2 years ago that made progress on that other conjecture, and by plugging it in, we were able to solve the original conjecture. So, it was a combination of just lots and lots of people, and the people who contributed were not all mathematicians, actually. So they were some were working in tech companies, some was a high school student, and they each had their own separate favorite AI tool, or some were working pen and paper, and together they were able to solve this problem. So I think this is kind of an example of this sort of breadth type approach to mathematics. So just to wrap up, AI has developed quite a lot, especially in the last year or so, and it's enabling ways to do new ways to do mathematics at unprecedented scales and speeds. I think what's going to happen in the next year or two is that people are going to start systematically collecting sets of problems to solve, or other sets of mathematical tasks to accomplish. I mean, basically, if you build it, they will come. And there's going to be a lot of community projects. I'm going to start a few myself at IPAM, where we have, we just set out lots and lots, a large number of mathematical things to do, and then you can get the community to crowdsource. They will solve, some portion of them. AI will solve some of them, not with 100% success rate, but that, you can still get a lot of mathematical progress out of that. And these tools really, really lower the barrier to math research. And so, I'm interacting with lots and lots of people mathematically that I wouldn't have in the past. So it is a very exciting time for mathematics. I think there's going to be a lot of change. So thank you very much.